Okay, so yeah, so figure out the protons, electrons, neutrons we talked about the other day, and so for the sodium we figured out there's 11 protons, 11 electrons, 12 neutrons. We figure out the neutrons based off the mass number and atomic numbers by subtracting them together. The electrons and protons are typically determined from the atomic number. Now, for a charged particle, so an ion in this case, if you have a positive charge like sodium does here, what you do is you subtract the electrons based off the charge. Now, if you have a negative charge, then you're going to add the electrons. Now, you say, well, how do I know how many electrons there are to add or subtract? Well, it's based off of the charge that you see right here. So in this case, it's +1. Now, the protons are going to stay the same. The neutrons are going to stay the same. The electrons, however, since it's +1, what you're going to do is you're going to do 11 minus 1, which gives you 10. Remember that if you're positive, all right, that's because you've lost an electron. So that's why we subtract electrons. If you're negative, that means you gained electrons. That's why we add the electrons. So another example would be oxygen, and this is coming straight from the periodic table. 16 and 8 are the atomic number, mass number on the periodic table, and then -2 is the charge of the ion. Now, the protons are still 8. The neutrons, 16 minus 8 gives you 8. And then the electrons, now this time the charge is -2. So since it's -2, you're going to add 2. So you'll have 10 electrons. Does everyone understand that?
Yes.
Okay, so if we were to look at phosphorus, all right, so looking at the periodic table, so phosphorus has a mass number of 31, and I'm just rounding this up here, and then a atomic number of 15. Now phosphorus could be a -3 charge. So for phosphorus, well, we're going to have 15 protons. For the neutrons, you're going to have 31 minus 15, which gives you 16 neutrons. And then for the electrons, well, since it has a -3 charge, you're going to do 15 plus 3, which gives me 18 electrons. And so now in the case of an isotope, what is the definition of an isotope? So isotopes are atoms of the same element that have different masses or differ in the number of neutrons. So it's their mass number changes. That mass number also changes the number of neutrons. But what you want to do is make sure you understand that the isotopes are of the same element, but they differ in the number of neutrons. Okay, so a great example is hydrogen. All right, hydrogen has 3 different isotopes. There is hydrogen 1, and this is how we would write it on paper. Hydrogen 2, and you have hydrogen 3. So when we write these in the form of the nuclear symbol. So hydrogen 1 has a mass number of 1. The atomic number for hydrogen is still 1. The nuclear symbol for the hydrogen 2 would be a mass number of 2, but still the atomic number stays 1. So that atomic number never changes. And then hydrogen 3 is mass number 3 with an atomic number 1. Now, when we look at protons, neutrons, and electrons, the protons for all 3 of these stay at 1 because that's based off the atomic number. It's the neutrons that change here. In fact, these are all the same charge, so the electrons remain the same with 1 electron. Now the neutron, you look at the mass number, subtract from the bottom number. So mass subtract from atomic, which gives you 0. This gives you 1, and then the bottom one gives you 2. So as you see with the neutrons, the isotopes vary by 1 neutron as you go from hydrogen 1 to hydrogen 3. All right, so that's what the difference is between just a normal atom that you find on the periodic table as compared to when we start looking at their isotopes. All right, and so you have to ask yourself the question, well, how many elements have these isotopes? Okay, so, and that's a tough question to answer. Most of your elements in the periodic table have a different number of isotopes. So I'm gonna pull up a table here. So this is a table that lists just a few elements on the periodic table. It shows what isotopes they have. It also shows their percent abundance. Now, percent abundance just represents how much is present on Earth. So when we look at hydrogen, we said hydrogen has 3 isotopes. Now, hydrogen 1 has a percent abundance of 99.99%. Pretty much all the hydrogen you see on Earth is represented by hydrogen 1. Now, hydrogen 2 has 0.02% abundance, and then hydrogen 3 is so small to the point where we just call it rare. There's not really any physical way of determining a numerical value. It's not worth the time, but it's still there. It's just an extremely small amount. Now, boron has 2 isotopes, so does carbon, and so boron has 2 isotopes where their percent abundance is 19.9 and 80.1. And then you can see on down the line, I don't have to read all these to you, but you can see all down the line that each of the elements has a different number of isotopes. And obviously sulfur has the most isotopes out of all the elements that are listed here. So there are books that are published that list all the different number of isotopes for each of the elements. We're not going to get into that. And so one thing that you ought to know is that you don't have to worry about memorizing these because these tables are provided to you. What you have to be able to do is use them and know how to use them. And so now when we talk about elements and the percent abundances, now when you look at the periodic table of elements and you see the mass number that is on that periodic table, that mass number is really based off the isotopes and averaging out their percent abundances with their mass numbers. So what we're going to do right now is I'm going to show you how we go about solving for the mass number that you see on the periodic table. And so we're going to use the values that we find in this table. So before we do that, I need to give you a basic equation. So what you probably ought to do is at least write that down right now. So I'm going to give you guys about 30 seconds or so. I want you to write that equation down. This is the equation how you solve for the mass number on the periodic table. So go ahead and write that down, please. All right, so how do we use this? So I'm just going to write it out first. And so looking at hydrogen, you have 3 isotopes. The third isotope doesn't matter, so we don't even need to worry about including it in the calculation. So the way we go about doing this calculation is you use the percent abundance. So we're looking at hydrogen 1 first. So we look at the first hydrogen, which has 99.99% divided by 100, because you want to get rid of the percentage, so you always divide by 100. And then we're going to multiply it by its mass number. Now, in this case, the isotope has a mass of 1. Now, that's the first isotope. Now we're going to look at the second isotope. The second isotope has a percent abundance of 0.02. We're going to divide that by 100, and we're going to multiply it by 2 because that's the molar mass. That's the mass number. So in this example, so what we want to do here is in your calculator. So make sure you use parentheses here. So 99.99 divided by 100 times 1 plus 0.02 divided by 100 times 2. So what we end up with is 1.0003. The unit for this would be AMU. AMU just stands for atomic mass unit. You only use this unit for isotopes, by the way. All right, so that's what that unit's for. All right, so anytime you do you calculate the molar, I keep saying molar mass. Anytime you keep calculating the atomic mass unit, you use those units from the isotopes. Okay, so you'll see why I keep talking about molar mass is because we use that a whole lot more than this. We very rarely use AMU. The only time you really use it is going to be on exam 1 when you're dealing with isotopes. So this is the way we solve for hydrogen. Now, if you look at your periodic table, hydrogen is actually 1.008. So it's not that we're wrong in the fact of the way we calculated it. We are using a rounded mass number. So all these masses that I circled here, those are rounded. If we were to use the exact isotopic mass, we would get what we see on the periodic table. So now right here, so what I pulled up is the isotopic masses. So we have 99.9, so that's what we see from the percent abundance. Now, this number here is the actual atomic mass for that isotope. It's not rounded. And then the second one, that's the mass number for the second isotope. So these are what are called exact isotopic masses. If you're ever given the exact masses, use them. Don't use the rounded number unless you have to use it. All right, like we did here in this example. So I wasn't provided the exact mass, so I'd have to use the rounded mass. So when you use the exact mass, look at what you get here. You get what you see here, which is 1.008, and that's just rounding that 7 up to an 8. So now you could do this for any of those isotopes, any of those elements. They utilize the same equation. So I'm going to do oxygen here, and so I want to provide you one more example. All right. So we're going to look at oxygen, and we're going to use what's given to us in the table here. All right. So to do oxygen, there are 3 isotopes here. So we're going to have oxygen. The first one is 99.76 divided by 100 times 16 plus 0.04 divided by 100 times 17 plus 0.2 divided by 100 times 18. All right, so we'll plug that into our calculator. So I'm going to do that right fast. So when I plug this in, I get 16.0044 AMU. Now so the next thing you have to say, okay, well, I got the number. Now in the book, oxygen is 16.00. So if you look at the percent abundances, all the percent abundances stop at 2 decimal places. So what I want to do is I'm going to stop at the second decimal place. So that's what I should get. This is my final answer here. for that. It's a 16.00 AMU. In fact, that matches what you see in the textbook. So that's how we calculate the mass number that you see on the periodic table using the isotopes and their percent abundances. Any questions on that?
Well, I have a question. For the percent of abundances, during the exam or quizzes or tests, will we be provided that?
Yes.
Okay.
I have a question as well. So if protons and neutrons and electrons are always supposed to have the same mass, then why is it that, for instance, the difference between hydrogen 1 and hydrogen 2, if you're only adding one neutron, you don't get an equal mass number?
I'm trying to understand what you're asking there.
So since protons and neutrons in the hydrogen example are supposed to have like a nearly identical mass, if you were to just take 1.0079 and multiply it by 2, it doesn't give you 2.014. It gives you like 2.0158 or so. So why are those numbers a little bit different? Do neutrons vary in their weight or mass rather?
Not necessarily. That's a good question. All these data points that we're getting here, so all the mass numbers and the percent abundances, they're all determined from analytical chemistry, and so they take these instruments and they'll run these samples through the instruments, and they'll do this multiple times. And typically, what happens is that they'll take the spectrum and they'll pull out the details from the spectrum, and they'll average those details between all of the data points that they collected for it. And that's typically where we get our numbers from. You know, what you're saying makes perfect sense. Why wouldn't it be taking the 1.0079 times 2? It's all determined from experiments and averaging out the data that you collect from the experiments. That makes sense?
Yeah.
All right. So we're going to move on here. And so, in fact, talking about that, so I'm not going to spend too much time on the slide. I'm just going to say that isotopes are determined from the mass to charge ratios. Lighter molecules come out faster, heavy molecules come out slower. So when you look at a graph here, hydrogen 1 is going to be a very tall peak, and then you have hydrogen 2 which is a small peak, and then hydrogen 3 is real tiny. So what they do is they take the mass, the charge, and they take the how tall this peak is compared to this one here, and that's how they figure out the percent abundances. The taller the peak, the more concentrated it is, the more abundant it is. So I'm not going to spend too much time because I'm not going to be asking questions about mass spectrometry on your test. So what I do have is a problem here that's a good example. I'm going to do the first column for you. So I'm going to do column 1 here, and there's 5 columns here. So I'll do column 1. So what you do is you take the information given to you and you figure out what the element is. You write the nuclear symbol along with the charge if it does have a charge. So to figure out if it has a charge or not, what I do is I look at the protons and electrons. Protons, your neutral part. So your electrons, if the electrons differ from the protons, you're going to have a charge. So in this case here, the protons and electrons are the same, so the net charge is 0. Now, if you're wondering what these ones are in the boxes, this is how many points that this box is worth. So if you wrote 0, I would give you 1 point. And so now what we next do is take the protons and we figure out what element we're dealing with. So we're dealing with element 5, so that is boron. All right, so you have boron. Now to figure out the mass number, what we do is we take 5 plus 6. You take those two, and that gives you what, 11? Yep, so 5 plus 6 is 11. And then the mass number, or the mass number is 11 because we add these two together. And then the protons is what gives you your atomic number, which is 5. Since the charge is 0, you don't write anything there. All right, so that's how this works. So let's do column 2 together, all right? So first of all, is there a charge?
Yes, it's 2.
Okay, so we know that the electrons are going to differ from the protons. So how many protons are we going to have here?
26.
Okay. Now, how many electrons? So it's plus 2. So do we add 2 or do we subtract
28.
2? No, it won't be 28. It's plus 2.
Wait.
It's opposite from what you typically think.
Oh.
So we need to
24.
subtract 2.
Yeah, so this will be 24. Exactly. Yeah. Now, how do we figure out the neutrons? You take the mass and subtract by the atomic number. So how many neutrons are we going to have here? Be fast, guys. 54 minus 26 is what?
$28.
Yeah. All right, so that's how we do. So we're done at this point. All right, so that's how we do that. So what I want y'all to do is I want you to do column 3. I'm gonna give you a minute to do it, starting now. All right, who wants to give me their answers? How many protons does this have?
It's got 15.
Okay, so 15. I'll agree to that. And what element symbol do we start with here?
pH, phosphorus.
All right, so it's P. Yep. So we know the charge is -3. That's given. So what's the mass number here? So
31.
Yep, 31. And then what's the atomic number?
The atomic number.
That's the easiest one. It's 15.
It's the third. Oh, wait.
Oh, sorry, I wasn't sure what you were asking. Yeah,
Well,
it's 15.
Okay, good. So we all on the same page here?
Yeah, I was thinking AMU for some reason.
Yeah, same.
Okay. All right. Yeah. So let's do column 4. I'm gonna give you another minute. So get started on it. All right, what you got? Anybody want to do it?
I'll do it.
Go for it.
It's gold, AU, And the mass is 197, and the number is 79, and it has no charge.
Okay, good. Great. Thank you. All right, number 5. Let's do it. So another minute. All right. So first question, what element are we looking at here?
Radon.
Okay, what's the symbol for radon?
Rn.
Okay. What's the mass number?
222.
Okay. And what is the atomic number?
86.
All right. So there's no charge, so how many electrons should it have?
Also 86.
All right, we're done. That's it. Does anybody have any questions? Does that make sense?
Yes.
Okay, good. So, all right, great. We're going to move on then. So this is the next problem here, and this deals with the isotopes, of course. This element is indium, and it has 2 isotopes. So what I want you to do is calculate the average mass number for this element. So you're given 3 different columns there. You're given the percent abundance, and you're given the isotope mass and its mass number. So obviously, this will be something that you use. Now, do you want to use this or do you want to use this? So which one do you think is the best method to use here? Would you use A or would you use B in your calculations? I asked that because B.
It's, yeah.
Yeah. So, all right, cool, good. So go ahead. I'm gonna give you guys a couple minutes to do this one. I'm actually gonna do it too. So go ahead and work out the answer, and we'll come back together in 2 minutes.
We use that same formula for this, right? The formula
Yes.
we showed? Okay.
Mm-hmm. And I want you guys to record to the 2nd decimal place. Okay, so I'm going to go ahead and put the answer on here to save a little bit of time. So the answer should be 114.82 AMU.
I got 114.91.
So what I did was I put 4.3 divided by 100 times 112.9041 plus 95.7 divided by 100 times 114.9039. What I got was 114.82, rounding up to that. So you might want to check your numbers just to make sure you didn't do something simple.
Okay, I see where I messed up.
Good, good. All right. So that's all I have.